So rational expressions. I'm going to go a little bit more detailed than I would do if I'm in college algebra. I don't know how much whoever you took that from did it, but I'm going to go a little bit more than what I normally do. Well, not a whole lot more. So, all right. So rational expressions. So this would be, or not rational expression, but rational functions. So a rational function, r of x, let's just call it r for now, is p of x divided by q of x, where p of x and q of x are polynomials. And q of x is not identically zero. It can be zero some spots, but not all, can't be everywhere. We mean, sometimes they write identically like this with three lines. It means it can't be zero all the time. All right. Or really, this is the better way to write it. And x is not equal to zero. It's not identically zero. It's not equal to zero for all x would be something for all x. That's what that symbol means. So here's some examples, right? So if I have f of x is equal to x squared plus 1 over x minus 1, like that, that's a rational expression. If I have something like 1 over x, that's a rational expression. If I do something like, let's say g of x is equal to 2x minus 1 over 2x plus 1, that's a rational expression. Now, they all have something slightly different about them, and that's what the degree is. So we're going to look at these, each one separately. So this would be where the degree of p, we'll call that the numerator, is less than the degree of the denominator, like that. That's one style. Here, the degree of the numerator is equal to the degree of the denominator. And here, the degree of the numerator is greater than the degree of the denominator, like that. So these are kind of the three things we're going to look at here. Now, there's one other thing that we're going to consider, and that's when there's the one thing you'll notice about all three of these that I've done is these are all irreducible. You can't factor anything out. But if I had something that looked like, say, x minus 1 times x plus 1 over x minus 1, notice that these things divide out, which will give me x plus 1. But the domain of this function still has to maintain this what's happening here. So this would be, remember, x cannot be 1 because it wouldn't be allowed in the original function. So what's the graph of this? Well, that's just a line that goes through 1, 0 like this. But at 1, there's a hole in the graph like that. So this is a graph of a line with a hole in it. And that's because of this thing right here. So if I have something like, let's try another one. Say I have f of x, we'll keep it really simple like this, x over x. Well, you can't have it be 0 because there's no such thing as 0 divided by 0. Otherwise, this is always equal to 1 as long as x is not 0, right? So we have the constant function with a hole in it and then keeps going like that. So anytime you have factors that divide out completely in the denominator, then you can look at what's left of the numerator and what's left of the function and graph it and then just stick holes in it. So even if it looked like something like f of x is equal to x over x squared, right? This thing, when x divides out, looks like this. So this graph will have a hole in it at 0, but this one won't be at 0 anyway, so it won't matter. So there's kind of some things you have to consider. All right, so things factor out, then we will have holes. Otherwise, we'll assume for a bit that what happens when we don't have things that factor out. So let's assume for discussion, right, that P over Q is in reduced form, right? So in other words, you can't factor anything else out of it. Now we can start talking about what the degrees mean and all that kind of stuff without worrying about holes in the graph. So in other words, no holes in the graph for now. We'll come back to that at some point. So there's no holes in the graph. We're just going to look at it. So the first thing let's do is we would look at, say, something called a vertical asymptote. Now, what an asymptote is an equation or the graph of an equation or function, right? It's the graph of an equation. The function gets arbitrarily close to. So that means that over time, the behavior begins to act like the other one. So a vertical asymptote would be x is equal to a constant because we're talking about a vertical line like this. All right, so our first type, and so let's go back to this one because this is 1 over x like this. So why is this important? Well, notice that in this example that the degree, well, I won't talk about that. That's horizontal. So vertical asymptote. This is connected to the domain of the function, right? So what's the domain of this function? The domain of f is the set of x's such that x is not 0, right? Because you can't divide by 0. Well, it turns out the vertical asymptote in this case, because there's no holes, is exactly where it can't be defined. So the vertical asymptote and this one are connected. So if I were to graph this thing, what happens is as we get closer and closer to 0, plug in x's, right? If I plug in 1/10, I get 10. If I put in 100th, I get 100. If I put in 1,000, I get 1,000. So thousandths, I get 1,000, like that. So it goes up. I messed it up. So from here, from 1, as I get close to 0, it begins to look like a horizontal line. On the other side, if I plug in, so like, right, if I plug in x, if I plug in 1/10, I get the reciprocal, which is 10. 100th, I get 100. 1,000, I get 1,000th, I get 1,000. Now, if I go the other side, if I put in negative 1/10, I get negative 10. If I put in negative 100th, I get negative 100. So you can see the same thing, but now it's going negative. So it's going this direction like this. So my function is going that way. This means that this value right here, x equals 0, which is not in the graph, is a vertical asymptote like this. So x equals 0 is our vertical asymptote that we get close to like that. Okay, so anytime the denominator is 0 and you can't divide it out, we're going to end up with a vertical asymptote like that. All right, so let's try, we'll come back to this. So let's try this one. Let's do the 3 that we had originally. So let's say we have, this one. G of x is 2x minus 1 over 2x plus 1. So again, the domain of G would be the set of x's such that if I plug in a negative 1/2 in here, I would be dividing by 0. So that means my vertical asymptote is x is equal to negative 1/2. So if I now go to my graph, here's say negative 1, here's 1, there's negative 1/2. So at negative 1/2, I'm going to get a vertical asymptote here, like this. I'll make it pink. It's easy to see, like that. So this is x is equal to negative 1/2. That's my vertical asymptote. So now what happens is I get closer to it. Well, if I put in numbers bigger than, now here's where rather than using tables, you can actually use a logic here, right? If I put in numbers that are bigger than 1, so let's do this. Let's make a little table. Here's negative 1/2. If I put in numbers that are bigger than negative 1/2, like say 0, then the top is going to be, oh, we need another point. We need 1/2 because that's where this one's going to be 0. That one's 0 there. That one's 0 there, like that. Now this is the vertical asymptote. So let's put a little triangle there. Or we could, since I was using pink, we'll put the pink line here. This one is 0. That's going to be where it crosses the x-axis. So that 0, because it's in the numerator, that's our x-intercept, like that. Okay, so now what's going to happen is if I take something that's negative, if it's less than 1/2, then in between 0, this thing is going to be negative. If it's a negative number, that's going to be negative. And same with this one. If I take something less than negative 1/2, this is going to be negative. But then this one will become positive, and then this one will become positive. Just like this one, if I take something bigger than 1/2, this one's going to be positive. All right, so what that means is that here at negative 1/2, in this little region right here, it's below the axis, and this is above, and this is above. So it looks like on this side of the graph, we get a positive. Why? And so what am I doing here? I'm actually dividing the two above, right? Like this. Negative divided by a negative is a positive. A negative divided by a positive is a negative. Positive divided by positive is positive. So over here, I get positive. So that means that I'm going to have to get close like this. My vertical asymptote has to look like that because it has to go positive. So it's going to have to go up. Now this part's going to have to be negative, the part just on this side of it. What I know, though, is that here at 1/2, it has to be 0. So this thing is going to have to go something like that. It's going to have to go from 0, and it's going to have to come more and more negative. It's going to have to act like that line, like that. So I have something acting in that fashion right there. All right. What's the third one? You know what? I'm going to save the third one and do it all at once. So now let's go back and look at something else, because these two have something in common, but slightly different from each other. The next thing we'll look at is called horizontal asymptote. Oh, and so notice here, this is one where the degree, in this case, the degree of the numerator is equal to the degree of the denominator. That's going to be important. Just like in this one here, the degree of the numerator, this is where the degrees come in. The degree of the numerator is less than the degree of the denominator. Horizontal asymptotes. You don't say the P. Okay, so now so that horizontal asymptote. So notice that the degree of the numerator is smaller than the degree of the denominator. So what happens? Well, this is just a reciprocal function, right? So if I plug in 10, I get out 1/10. If I plug in 100, I get 1/100. But notice the sign never changes. So what happens is that when I'm going from 10th to so if I did it in a table, like if I plugged in X, I would get 0.1. If I plugged in 100, I get 0.01. If I plugged in 1,000, I'd get 0.001. If I plugged in 10,000, I get 0.0001. So notice that the sign never changes, but I'm getting closer and closer to 0. So this is going like this. It's getting really close to it, but not ever touching it. Same thing if I throw negatives on here, these become negatives. So this thing is going to come and get arbitrarily close to the x-axis like that. So it tells me that this horizontal line here, that never crosses it and it never touches it, but it gets really close to it. This is our horizontal asymptote. It's y is equal to 0, like that. All right, so now this one's a little different. When the degrees are equal to each other, what do I want to happen? Well, notice that what's happening up in this one is that the degree of the numerator is 0, and this one is bigger. So that means that the bottom is dominating the top and it's crushing it out to 0. Here, because the degrees are the same, you have that neither one dominates the other one. In time, they dominate this. So what that means is that 2x minus 1 over 2x plus 1, eventually they're going to look a lot like 2x over 2x, which these numbers divide out. Well, those do 2, and you get 1. So this thing's going to have a horizontal asymptote at 1. In fact, if these numbers were different, like 2 and 3, then it'd be at 2/3. So it turns out that your horizontal asymptote, when the degrees are equal to each other, is going to be the y is equal to whatever the lead coefficient of one polynomial over the other one is. The ratio of the lead coefficients, in this case 2 over 2, which is 1. So at 1, we have the line y equals 1 here, and this thing is getting close to it both directions, like that, as I move away from it. And I get my horizontal asymptotes like that. All right, let me try another one. So, or another couple. So let's say we have something like f of x is equal to, I don't know, let's try x minus 1 over x squared minus 9, like this. All right, so vertical asymptotes, it's kind of connected to the domain. So where is the denominator equal to 0? Well, x squared is equal to 9. X is equal to plus and minus 3. So there's my vertical asymptotes, because I can't factor that out. I could also do it like factor this thing, right? Because the bottom factors to x plus 3, which is helpful. There's my plus and minus. There's my, 3 and minus 3 give me my vertical asymptotes. So I have 1, 2, 3, 1, 2, 3. So x equals negative 3. X equals 3. So there's my vertical asymptotes, like that. Now, the degree of the numerator is 1. The degree of the denominator is 2, which means it dominates. So that tells me I have horizontal asymptotes as you go to 0. So out like that, they go to 0. Now, what else do I, so my horizontal asymptote is y is equal to 0. Now, what else do I know? Well, if I look at the numerator, x minus 1, set that equal to 0, I get x equals 1. So at the point 1, 0, I have to go through the axis. So this is my 0 for the function is x is equal to 1, right? Or the x-intercept is 1, 0. What about the y-intercept? The y-intercept is, well, just plug that in. 0 over 1 and 0 squared minus 9 is 1/9. So there's some spot right here that it has to go through at 1/9. Now, the other thing that we can use is that polynomial stuff, right? The degree of this thing is 1, right? The multiplicity, so the multiplicity of that 0 is 1. So I know it has to go through. So since it has to go from here to here, I know it has to be something like that. Now, can it turn and go up? No, because there's no other 0, so it can't cross the x-axis again. So, and I know it has to get clear next to the vertical, so I have to continue going closer and closer. So I get something that looks like that. Now, what about this side? Can it turn and go down? No, because this is the only 0. It can only cross the x-axis at that one spot. So this thing is going to have to go up like that, get closer that way. All right, now out here, there's two possibilities. Since it never crosses the axis, it's either going to be, just to give you an idea, I either am going to have top or bottom. So you can't have both of these, right? It has to be one or the other. Can't have something that looks like this, that goes across somehow, that crosses it and comes back up. It has to stay entirely in that little quadrant. So all we really need to do is pick a number and plug it in and see what sign it is. So let's say this is 3, so let's put in 4. So if I took f of 4, that'd be 4 minus 1 over 4 squared minus 9. That's 3 over 16 minus 9. Now I could keep figuring it out, but why bother? All I care about is if it's positive or negative. Well, that's positive. So at 4, it's up here. So that means that tells me that